So today we're going to be talking about subsequences. And so again, I'm going to follow the presentation from a different book. This is again that book of, let's call it Friendly Introduction to Analysis. So subsequences. You have some sequence, and then you have let n sub k be a sequence of positive integers where they are increasing. Okay. So you have some sequence. Then we call a sub nk a subsequence. So sequence of a sub n. Okay. Okay. So this n sub k is just a just a selection of indices. You have one sequence, and then you're selecting various indices from the original sequence, and you call those corresponding guys a subsequence. Okay, so for example, there's some simple examples. If you have a sequence a sub n is 1 over n, you could take n sub k to be k squared. Right, then your sequence a sub nk is going to be, a1, a4, a9, a16, etc. Right, so it chooses the 1 over 1, 1 over 4, 1 over 9, 1 over 16, etc. Right. Example number 2. -1 to the n. Let's choose n sub k to be 2k, say. Then your a sub nk is just the guys with even indices, right? From the a2, a4, a6, a8, blah blah blah. And of course, those are the guys who are all ones. Okay. Okay, so the notion of a subsequence, is nothing very fancy, right? You've got a sequence, and you're just selecting elements of that, you're selecting elements of that sequence with increasing indices, and the main thing is just to become comfortable with the notation of it, right? So usually people use this sort of double index, right, to indicate that you have this. This is a sequence. This is a sequence of indices that you select from the original sequence. Okay, so it's not a great idea. It's not a huge idea, but it's a convenient one. Okay, so let's prove something let's make a very simple observation about subsequences and convergence. So a sub n converges to L if and only if. What do you think I'm going to say on the other side? One subsequence? Every subsequence, yeah. So every subsequence converges also to L. Okay, now one direction is easy, right? If every subsequence converges to L, then certainly the sequence itself converges to L, right? Because you just take your subsequence to be the full sequence, right? Just take your k to be n. Take your k to be k. I'm sorry, take your n sub k to be n. No, to be k. Excuse me. Right, so since every subsequence converges, the full sequence converges. Because you consider the full sequence to be a subsequence of itself. Okay. Now the opposite direction is well. Let me. Why don't you try for 1 minute to write down how would you write that down? So you know that for all epsilon greater than 0, there exists an n such that if you're past that n, a sub n minus L is less than epsilon. Right? How does that? Why does that show that every subsequence converges to L? It's just a matter of notation, I'd say. So think about it for a minute and see if you can write down the argument.
Does that mean no?
You know, so we already know. Right, we're given that for all epsilon greater than 0, we're given that a sub n converges to L. Now let's show that every subsequence converges to L. So let a sub nk be an arbitrary subsequence of a sub n. And let's see that one also converges to L. Okay, talk to somebody nearby, please. Also, my wife has given me a bunch of candy. If anybody wants some candy, you can have it. Somebody wants it. Oh, yeah. Well, let me see if you have it.
Yeah, I'm just kidding.
Oh, wait, but you're cooking at Patty. Okay, everybody wants candy.
It's for all animal
Yes. My daughter's allergic to milk, so she can't eat any of that. Yeah. And then there's some peanuts, and neither of my older children can eat that. Don't worry, I'll also offer it to the next class. So, okay, so what's the idea? the idea is pretty simple, right? Or what's the idea? You have a subsequence. You already know that there's some time past which, all the a sub n's are within epsilon of L. You're trying to show that there is some, can somebody tell me what you're trying to show? You want to show what?
A sub nk minus L is less than epsilon.
Yeah, so a sub nk minus L is less than epsilon. You want to show that there exists some, what? Some n, let me use a different number.
N1.
I'll use a k.
Push that for all nk bigger than k.
Not exactly, such that for all, such that if k is bigger than k, right? So this is the thing about getting used to the notation, right? The index for the subsequence is k, right? K goes from one to infinity, right? It's nothing complicated, but you just have to say we want to choose the index for this thing is k goes from 1 to infinity, right? So you're looking for a k such that if the index is bigger than that, then these guys are within epsilon of L. Okay, and so how do you find the k? What k do you choose? Well, you already know that there is an n such that if these guys are bigger than n, then everybody's within epsilon of L. So anyone see it? If you see it, I'll give you a piece of candy. No, I'm joking. I already gave you the candy. Does anyone see how to phrase it properly? Right. We already know that. So how do we choose our k? Raleigh?
Shouldn't it be just n?
Eh?
Shouldn't it be just n?
Should it just be n? Let's see. Should k equal n? Right then, if okay, then you're saying that a sub nk minus L is less than epsilon? Why? Why does that follow?
Well, because we already know that for all times past n, this holds.
Yeah, so is nk, what you're saying is that then n sub k is bigger than n, and so a sub nk is minus L is less than epsilon. Right, so this is the thing that I want you to make a little bit clearer. Why is n sub k bigger than n?
Because it's an increasing sequence.
Yeah. Okay. So you could say, well, look. N sub k is an increasing sequence. N sub k is an increasing sequence. So n sub k is bigger than k, right? So then, if k is bigger than k, sorry, I should write this. If k is bigger than k, then n sub k is bigger than capital K, which is equal to n, right? So bigger than capital K, which equals n, and so all these guys will be past the time that we're looking for. Okay, so that's one way. So take k equal to n. you guys see what Raleigh is saying? That suppose the good time that you want to be passed is time 5, right? Well, if you take k to be 5, then you know that you've got n1, n2, n3, n4, n5, and that they're increasing, right? Right. But then n5 definitely has to be bigger than 5, right? So n5 has to be bigger than 5. So as long as your subsequences index is bigger than 5, then the original index is going to be bigger than 5 also. You could do it a slightly different way. So maybe, I don't know if this will be clear or less clear, but you could go like this. Choose any k such that n sub k, n sub capital K is bigger than n. Choose any k naught such that n sub k naught is bigger than n. Right. It may be that your subsequences indices are jumping very fast. Okay. Well, just choose any one where n sub k naught is bigger than n. Right. Then, if k is bigger than k naught, certainly n sub k is going to be bigger than n sub k naught, which is bigger than n. And so a sub and k minus L would be smaller than epsilon. Okay, so either this way. So from this point here, you could either go this way, or you could go this way. Okay, either of those will be appropriate endings. Is this clear to everybody? Anybody have questions? You guys are looking a little blank. Chen? No questions? You good? John? You clear? Okay. Chen? Okay. So this is a very sort of trivial statement. It's just a sort of a notation game, but it has some useful consequences. For example, if any subsequences diverge, then you know that the full sequence diverges, right? The sequence diverges, right? Because convergence would ensure that every subsequence converges. Okay. Another consequence, right? If two subsequences have different limits, then the original sequence diverges. Okay, and 3, if a sequence converges, then we can use subsequences to determine its limit. Right? because you find some subsequences, some subsequence that converges, you know that the full sequence is going to converge to that. So just some, you know, pretty obvious consequences. And those lead to following notions. If you have a sequence, and let's suppose that A sub nk is a convergent subsequence, then let's say converges to some alpha. Okay. Then we call alpha a subsequential limit. Of the sequence. Okay. So it's just a limit of a subsequence. Now I'm going to give a definition that maybe you'll like a little bit better. The limsup of a sequence is actually the supremum of the collection of subsequential limits. Of the sequence. Okay. So remember we had this notion of limsup before. Does anyone remember what the limsup, how we defined the limsup before? So limit as n goes to infinity. Like the limsup of A sub n, previously we defined like this: the limit of the supremums of A sub k, where k exceeds n. Right? Do you remember that? We looked at the, you look at the tail, right? You look at the tail past n. You take the supremum of those guys, right? And then you let n go to infinity. So you take tails that go on, that start farther and farther on, right? And remember those. Since you're taking a supremum over smaller sets, that's a decreasing sequence. Right? It's a decreasing sequence, and if the set, remember we did this for bounded sequences initially. Since it's a bounded sequence, then that's bounded below, and so this is going to have a limit, right, by the monotone convergence theorem. Okay. So that's how we defined the limsup before. But there's actually another definition that I mentioned at the time. There's a maybe more satisfying definition, and I kind of like this one better. It's the supremum of the set of subsequential limits of your sequence. Okay, so you look at your sequence and you look at all the subsequences there, see what limits they have, and then take the supremum of those guys, and that's the limsup. It's sort of more intuitive than this, limit of increasing of smaller and smaller tails. Limit of the supremum of the smaller and smaller tails. And similarly, the inf, right, is going to be the inferior set of subsequential limits. So I might give it to you as an exercise to show that these are the same. I don't think it's hard to do, but let me look at it, and maybe that'll be part of your homework to show that these definitions, our old definitions, agree with the new definitions. Yeah, Ronnie.
In practice, how do you find the set of all subsequential limits of A, since there are even many subsequences?
Yeah, it's not so easy to do, right? But if it's something simple, then it's possible, right? Like, if you have something like say, 1 plus 1 over n, negative 1 over n. Suppose you have some sequence like this. Right? So, you have some sequence like this. Here's 0 plus 1. Maybe the first one is 1 plus 1 over n. The second one is negative 1 over n. The third one is 1 plus 1 over n. The fourth one is negative 1 over n. And so you have this thing, and it's pretty clear that what you have this upper sequence declining to 1. You have a lower sequence, increasing to 0, right? And if you look at, there's basically only two subsequential limits, 0 and 1, and so this thing would be the limsup, and this thing would be the lim_inf, right? So you've got this lower sequence coming upwards, you've got this upper sequence coming downwards down to 1, and the lower sequence is going upwards to 0. So, sometimes you can use it, and sometimes you can't. Another thing which I almost certainly will do as homework is the following exercise. That the limsup and the limit are themselves subsequential limits. They are included in the set of subsequential limits themselves. Okay, so next important idea is the Bolzano-Weierstrass theorem for sequences. And this is usually how people think of the Bolzano-Weierstrass theorem. If you have A sub n, a sequence of real numbers, if that sequence is bounded, then you're guaranteed that it has a convergent subsequence. Okay, so any bounded sequence has a convergent subsequence. Okay, why does that make sense? Can somebody give me sort of an intuitive idea of how that's going to work out? Right, you have a bounded sequence. Why are you guaranteed a convergent subsequence? Can anyone think of sort of why this ought to happen? So let me break it into a couple of cases. You could break it into cases where, again, we'll let S be the collection of values. The set of values obtained by the sequence. Okay. And again, we'll break it into two cases. Either there's a finite number of values or there's an infinite number of values. Okay. Can anyone give us sort of a strategy for why either one of these is going to have, in either case, you're going to have a convergent subsequence. I'll let you think about it for 2 minutes, and then I'll ask you. Okay, talk to somebody for a minute, and then.
It's similar. Because the second part that you just mentioned is This is really important.
Okay, so why? Let's look at the first one, or whichever one people want to talk about. Does anyone want to talk about the first one? No? Me, you looked at me. Nope. Yi-chan, you're not looking at me. Do you want to say anything? Yi-chan?
We are talking about like using the Bolzano-Weierstrass for the accumulation.
Okay, so that would be for the second one, right? Do you want to say anything about the first one? Or do you want to talk about the second one?
I haven't think about the first.
You haven't thought about the first one? Okay, that's all right. Has anyone thought about the first one? So here's the idea for the first one, if nobody wants to say Okay, so think like this. Suppose there are only two values taken, right? So you've got an infinite sequence, and they take only these two values, right? Well, then what are you guaranteed a convergent subsequence? What's going to happen? What's going to happen? Well, at least one of these values has to be hit infinitely many times, right? Right? Because if they're all hit finitely many times, then you have only an infinite sequence, right? So, right, your sequence. So let's say that the values are v1 to vk are the values taken, right? Since we have an infinite sequence, at least one of the vk must be attained by infinitely many of the a sub n, right? You can think of it as some sort of pigeonhole principle, right? There's a bunch of pigeonholes. There's a bunch of pigeonholes, right? And you've got infinitely many pigeons. Well, one of these holes must contain infinitely many pigeons, right? They can't all have finitely many pigeons in them. So this is my so-called pigeonhole principle. Okay. So, well, since infinitely many of them attain it, just take those guys as your subsequence, right? Take those, those a sub n form a constant subsequence. Right? A subsequence where all the values are the same. Right, so attained by infinitely many a sub n, call them a sub n k. A sub n k, where the k and k are increasing. Right. And then that a sub n k is that a sub n k is a constant subsequence. Yeah, well.
Do you think to get a rule for the sequence, does it some kind of closed form? So formula how to generate each member of the sequence?
No, you don't.
You can just take any line amount and say this is a subsequence.
Yeah. You just say, well, look, choose each. I mean, you could, if you wanted to, you could write down a rule. Choose the first one that where vk is obtained. Call that one a sub n1, and then so on and so forth. Right? Go to the next one, right? But it's pretty clear that you can do it. I guess to be proper, you probably should write down a rule. But it's pretty clear that you've got infinitely many of them, so just use them as your sequence.
Right, but technically to generate the subsequence, you should have a rule in order to.
No. This would suffice. This would suffice. Yeah. You don't need to specify how. This would suffice actually. Okay. So what about for the other one? Sorry, we're starting to run out of time here. For the other one, Yichen, you said, well, let's use let's use the Bolzano-Weierstrass for sets, right? You know that by Bolzano-Weierstrass for sets, S has an accumulation point, accumulation point L, say, right? And so there's this L, right? And now you want to, now I think you really do need to start making a more precise rule. How would you create a subsequence that converges to this L? How do you create a subsequence? So you know that there's infinitely many guys, and that in any epsilon neighborhood, there's going to be, you know, guys inside the punctured epsilon neighborhood, right? So how do you create a subsequence out of those facts, a subsequence that converges to L? Okay. Actually, this is part of your homework, so I'm not gonna say. Okay. So let's just stop there, since we're running over time anyway.